In this video, we are going to be deriving an expression for numerical aperture. What is numerical aperture? Numerical aperture is a sign of an acceptance angle. So what do you mean by acceptance angle? The acceptance angle is nothing but it is the angle above which the whatever the light information sent in the into the optical fiber will be totally internal reflecting, and the light will be penetrated from the one end to the another end in the form of the optics. So here what is happening, whenever the light moves from the denser medium to the rarer medium, the light will be bouncing back to the same medium. So as this light is bouncing back, that phenomena we call it as total internal reflection. Now we are going to be considering the refractive index of two mediums. The first one is core, where the core will be always having a refractive index of a n1, where the core is the center part of an optical fiber, where whatever the light information we are going to be sending, that will be reflected bouncing back in this particular core medium, and followed by there is another layer which will be having a less refractive index compared to the core, that is named as n2. So n2 will be the refractive index of a cladding in the optical fiber. And the surrounding medium where the optical fiber is placed, it is considered as n0, so which is the refractive index of an surrounding medium. Now whenever the light is moving from outside medium to the core medium, the outside medium is considered as a rarer medium, and the inside medium we call it as a denser medium. The light will be refracting, and the refracted light will be moving towards the axis. So where theta naught is the angle of incident and theta 1 is the representation of angle of reflection. If I apply a Snell's law for the point O, then the Snell's law can be written as refractive index of an outside medium n0 to sine of angle of incident. Here the sine of angle of incident is theta naught because the light is moving from the outside medium, which is equal to the refractive index of a core medium, which is named as n1, and sine of angle of reflection. So here the reflection is theta 1 at the point O. So if I take this equation in the form of sine theta naught, which is equal to n1 divided by n2 into sine theta 1. So let me take it as the equation number 1. Similarly, the light which has been moved inside the core will be once again moving towards a core medium to the cladding. By applying a Snell's law at the point X, we are going to be getting another equation where X is the point where the light is moving and forming an angle of incident, where the angle of incident is given by 90 minus theta 1 and the point. That will be the angle of incident when the total internal reflection should be taken place. The light should be moved from denser medium to the rarer medium. So here now the core is acting like a denser medium and the cladding is acting like a rarer medium, which will be forming a 90 degree as a refracted light. So n1 sine 90 minus theta 1 which is equal to n2, the refractive index of a cladding, into sine of 90 degree. That is the minimum angle which is required for the total internal reflection. Now we know that sine of 90 degree is always equal to 1. Similarly, by a trigonometry, sine of 90 degree minus theta will be always considered as cos theta. So now we are applying that equation in the condition, and I can write this equation as cos theta 1. So by applying this to sine 90 value and as well as sine 90 minus theta 1, now the equation will become n1 into cos theta 1, which will equal to n2 sine 90 is equal to 1, so that's why I am taking it as a 1. Now by rearranging the equation, cos theta 1 will be equal to n2 divided by n1. So take it as equation number 2. Now I will be using a fundamental trigonometry equation where sine square theta plus cos square theta is equal to 1. So this equation I will be writing the entire equation in terms of a sine value in the form of sine theta 1 to replace the sine theta 1 position. So this equation, if I rearrange, sine theta is equal to square root of 1 minus cos square theta. So this equation I will be applying it in the equation number 1, where there is a sine theta 1. In that position I will be replacing this equation. Then the equation will become sine theta naught is equal to n1 divided by n naught, and the sine theta 1 value will be replaced as square root of 1 minus cos square theta 1. Now by using equation number 2 in the above equation, so we are going to be replacing a cos theta value as n2 divided by n1 in the above equation, where the equation will changes to sine theta 1 theta naught is equal to n1 divided by n naught square root of 1 minus the cos value will be square now n2 square divided by n1 square. Now whatever the terms it is in a denominator will be taken LCM inside the square, and the value will become sine theta naught is equal to n1 divided by n naught square root of n1 square minus n2 square divided by n1. Since the square root of n1 square and square root get cancels, and the remaining is n1. n1 and n1 will cancel in the equation, and sine theta naught will be equal to square root of n1 square minus n2 square divided by n naught. So according to this equation, the sine theta naught is a sine of acceptance angle which is equal to the numerical aperture as we discussed in the definition. So if I start replacing a sine theta naught value as a numerical aperture, then the equation will be numerical aperture is equal to square root of n1 square minus n2 square divided by n naught, where n1 is the refractive index of a core and n2 will be the refractive index of cladding and n0 will be the refractive index of a surrounding medium. What if the surrounding medium will be a air? You know that the refractive index of a air medium is always equal to 1. So n0 value will be replaced with 1. The remaining is numerical aperture is equal to n1 square minus n2 square. Why? Because this equation, the air medium's refractive index will be always equal to 1.